I get asked a lot of questions about gas chromatography, and one of them is frequently this one. Why do I see two peaks on an EtOH analysis using headspace gas chromatography flame ionization detector? And this is a frequent question asked by criminal defense attorneys all across the United States. Typically in the analysis of an accused motorist's blood for EtOH composition, meaning his or her blood alcohol content, by way of headspace gas chromatography with flame ionization detector, we will see two peaks if EtOH is alleged to be present. It can look like literally just two peaks on the chromatogram. So the question is, what is that second peak? The two peaks exist because in the method, the analyst uses what's referred to as an internal standard, or ISTD. An ISTD is a known and static amount of the analyte that is purposefully spiked or added to the solution, meaning blood. In other words, it goes into every single headspace vial in the run unless it's a true blank, meaning an aqueous blank. It is added during sample preparation time using volumetric delivery devices such as pipettes. The challenge to using the ISTD methods is to find an analyte that is similar to but not likely organically present within the blood. This is why EtOH determination will use N-propanol, because it's generally used as the ISTD. N-propanol's chemical formula is CH3CH2CH2OH, and therefore structurally similar to EtOH, which is CH3CH2OH, and is another type of alcohol. It's just a CH2 different. As a result, as gas chromatography is primarily a separation technique based upon boiling point and polarity in conjunction with the analyte's affinity for the particular stationary phase of the column, the two compounds, EtOH and N-propanol, which is the internal standard, will be easily separated with significant or sufficient resolution, meaning separation, as seen in most chromatograms if the method is correct. With most GC columns used for EtOH determination, N-propanol will elute, which means come out, or second in time over that of EtOH. What makes N-propanol a, quote, good selection to use as an internal standard is that it is primarily used as a solvent in the pharmaceutical industry and for resins and cellulose esters, and therefore is not typically naturally present in a living human being. It is, however, part of the body's natural cellular decomposition that occurs after death. So N-propanol would be a poor choice for EtOH analysis in post-mortem blood. Instead, methylethyl ketone is preferred. So why use the internal standard method at all? The purpose of adding this known and static amount is to help ensure accuracy, meaning attempting to ensure against deviations of bias. By adding this known and static amount of ISTD, we can try to guard against pipetting errors in the sample preparation phase that without the ISTD would cause error. In the GC run, there should be an N-propanol blank that looks like nothing but a single peak. In a well-designed method, this N-propanol blank serves really two purposes. First, it exists as a, quote, retention time lock, end quote, and this is for a qualitative measure and quality control. In our example that we talked about, the one peak, the machine is now taught that anything that elutes or comes out during the 2.470 minute period must be N-propanol and N-propanol alone. Of course, this idea of uniqueness due to a GC column is, of course, may not be true, as there are over 56 million organic and inorganic substances and 62 million sequences registered in CAS or CAS, but nevertheless, this is what the machine is taught. Second purpose, the area count of that peak serves as the amount that is the, quote, area count target amount, or the amount that we want and expect if there's good pipetting and good injecting by the analyst. It becomes our standard amount against which we compare all other chromatograms. The area count, for example, could be 43916, and that's the area count if everything is done, quote, right, meaning that it is static and known amount is added to each and every single headspace file. So we can literally flip through from chromatogram to chromatogram of each chromatogram within the run to see if it differs from that 43916 amount. If there's no deviation from the area count amount from the N-propanol from chromatogram to chromatogram, which would mean that there was no deviation adding N-propanol to the vial, from vial to vial, no pipetting errors, and is dead on precise with our delivery of N-propanol. However, that isn't the normal case. the normal case, even with the most conscientious person, there will be deviation. Not even the most perfect machine, even with the perfect analysis, will be able to deliver exactly the same amount of N-propanol into each headspace vial. It just can't happen. There's going to be variation. However, the big question is, if there's significant enough deviation, each method should have a well-defined, meaning in its instructions, what that means. In this ISTD area count number that we came up with, for example, 43916, this is if there's any sort of deviation where the correction occurs. If the chromatograms show deviation in the remaining vials that are analyzed away from this 43916 number, then a ratio correction occurs where everything is scaled up or down to get to the, quote, normal amount, or what we call our area count target amount. So if there is, quote, too much in the area count when we measure the next vial when it comes and it looks at the N-propanol amount, it reduces the N-propanol until it comes into that normal range. This resulting reduction is then calculated and becomes a ratio. But it doesn't just stop correcting at the N-propanol amount, it similarly reduces any other analyte detected by the same correction ratio. So if there's 20% too much N-propanol detected, meaning beyond the area count, then the N-propanol and everything else detected, including the EtOH, is reduced by 20%. If there's too little of the N-propanol is scaled up to normal, and every other analyte is also scaled up by the same ratio. So if there's 20% too little N-propanol detected, and then the N-propanol and everything else, including EtOH, is increased by 20%. In short, if the area count for the ISTD remains constantly the same, meaning that there's not outside the acceptable criteria as defined in the instructions, then there's no problem that needs a ratio correction to account for. However, if there's significant deviation as defined by that instruction, then ratio correction is applied across the sample and everything detected. Therefore, the key measure in terms of bias control in the analysis is the measurement of the ISTD, which in the case of EtOH determination is N-propanol. But guess what? They don't ever set up a calibration curve with the ISTD, and in terms of the method evaluation, there's no calibration curve. As we can see, the ability of the detector to correctly quantify the N-propanol is paramount, but guess what they never do? You got it. They never run a calibration curve for N-propanol. As we discussed before in our other blog posts that are there, that there can be a massive amount of deviation. And so the big question at the end of the day is, why don't you set up a calibration curve? Because without establishing a demonstrated linear dynamic range using certified reference materials on a well-constructed 5x5 calibration curve, then any measure that is other than the, quote, area count target amount for the N-propanol and then applying some sort of ratio correction as described like we just went over is just plain scientifically wrong. A single point calibration curve, which is really what happens in our example there in that scenario with 43916, is scientifically wrong. It presumes that any other measure on either side of that equation is both accurate and precise, which is not necessarily the case. It needs to be demonstrated. Until they start doing this right and demonstrating scientifically the linearity of their response in the measure of the internal standard on the flame ionization detector, then forensic laboratories are science.